Welcome everyone to the VK tutorial session of Galois theory MA70. Today we'll discuss some questions related to Galois extensions. So let's begin. Okay. So it is given that P be a prime number and let L be a splitting field of x raised to power P minus 2 belongs to Qx. So coefficients are in Q. First we need to show that L is equal to QA eta P, where A belongs to L with A raised to power P is equal to 2 and eta P belongs to L is a primitive pth root of unity. So P is given to be a prime number and L is the splitting field of x raised to power P minus 2 in Qx. So what is the splitting field? Like by definition, a splitting field
it is the field extension of type in which the given polynomial split into linear factor completely.
Exactly. So and this is the of that, like, so we can always say the smallest subfield, smallest field, or okay, smallest subfield of I'm just taking, let's say, C or anything for now. Let's say C because we know roots are there, any extension of Q if we consider. So smallest subfield of C containing such that containing all the roots of the polynomial x raised to power P minus 2, and as you said, smallest subfield of C containing all the roots of course, containing Q and, or maybe smallest Q subfield I can write, sorry. Containing all the, or not containing, in which the polynomial x raised to power P minus 2 is splits into linear factors. Exactly, very good. Okay, so we have L is given to be this. So now it is asked what is we have to prove that L is exactly equal to Q A comma zeta P, where L belongs to L with A raised to power P is equal to 2. So let's write it down. So to show, or maybe let A raised to power P is equal to 2, A belongs to L, be such that A raised to power P is equal to 2 as given, and eta denotes eta with the primitive nth primitive pth root of unity zeta P. Okay, so primitive pth root of unity means zeta P raised to power P is equal to 1. It is a pth root, and so firstly this is a pth root, second it is a primitive pth root of unity. What does this mean? What can I say? Yeah.
This pth root primitive means this root can generate all the
roots of unity. Exactly, very good. So what we can write, this is exactly, so we can say order of zeta P is equal to okay, so is equal to P minus 1, because that is no, it's fine. Yeah, so order of zeta P is equal to P. That means in in unity set. So this set un. Okay, this is the notation for up for here it is up. Okay, so this denotes the set of set of pth roots of unity. Okay, of course subset of C. So this is so it of course that means it can generate all the roots of unity. Okay, so this is the case. Now what do we have? Okay, so to show L is equal to Q A comma zeta p. So, that means like this is the splitting field of x raised to power p minus 2. Okay, so let's try to prove that. So what are the requirements to say that this is the splitting field? Like it should be smallest, it should and x raised to power p minus 2 should split into linear factors. So let's observe what is x raised to power p minus 2. What are all the roots of x raised to power p minus 2? Do we know?
Yes,
Yeah.
p power of 2 into root of unity.
Come again.
Pth power of 2.
Pth root of 2.
Pth root, sorry, pth.
Yeah, and
Yes,
that
pth.
is given. That is a. So a raised to power p is equal to 2. So a is such that a raised to power p is equal to 2. So we
Is
have.
the
So
is the pth root of 2.
Yeah, exactly. This is one of the roots, so we don't care. But a is certainly a root of pth root of 2.
Yes.
Okay, so for example it could be like pth root of 2 and something. So not all the roots looks like that, right? So yeah, a is given to be that. So and what are other roots? So as you can see, zeta is given to be it is given here. So we can try it out. What does this mean? So for example, if we try this multiplication, then if we do so if we want to check that whether it is a root of this polynomial, we have to just put it up in place of x and check if it gives 0 or not. So let's see, this is a raised to power p zeta raised to power p minus 2. A raised to power p is given to be 2. So this is 2, and zeta raised to power p would be what? This is a pth root of, so okay, sometimes I forget what is p. So zeta p denotes pth root of unity. If we write zeta n, it is like nth root of unity. Okay, so a raised to power p is 2, this is 1, this is 2, so this is 0, right? So that means x raised to power okay, so a is a root, and we have seen this is also a root. And what are all the roots we can check? We can check the because if you see, if we just have some any nth root of unity in at this place, we can this will just give 1, its contribution, the pth, if we power it to p, then we will get 1. So it will still give 0. So we can try all the pth roots, right? Pth roots of unity. What does this mean? You take a square, again you will get this, sorry, square and this. So a raised to power p is 2 into 1 minus 2, again this is 0. So in general you can try any power k, and till what? 0 to p minus 1, because 0 you have tried, which is a. So a is there, a eta p is there, a zeta p square, and up to and so on a zeta p raised to power p minus 1. I am considering only till p minus 1 because all the other roots, so zeta p raised to power p is 1, so I have to stop here. So again I'll get back a. So these are all we can have, right? Is that okay, this step?
Okay. Okay.
Okay. Okay. Okay, zeta p raised to power p is equal to 1. Okay, so we have this. Now also note that these are all different. This cannot be these cannot be the same, because firstly this UP group. So UP is basically what? If you remember, that is this, right? Corresponding, this is isomorphic to. So what is this? This means units of uh, okay, so what I mean to write, you go till zeta p raised to power p minus 1 and you will get 1. So this is this set, and its cardinality is p minus 1, right? If you remember, this is also on week 8 some not introduction, some revision is there of this, so it is there also. So UP is given to be UP is the set of pth roots of unity, and which you have already seen. These are all different. So yeah. Any doubts?
No.
Okay. Okay, so we have this now. Now if a eta p is I, this is same as this, or maybe j, then since a is non-zero, these has to be the same, because you are in a field, you can divide by a inverse and all this thing. So in turn these are all different. So v of x raised to power p minus 2, let's say in not in L, okay, we can say L because that is a splitting field, we already know. So this set is at least this. Also if you see, these are p elements, so we already have p roots, and this equation is x raised to power p minus 2. So in a field we know that any the number of zeros will be the count of number of zeros will be less than or equal to the degree of the polynomial, that is p. So we have this condition. So these are all roots of x raised to power p minus 2. Is that okay till this step?
Ma'am, VL x to the power p minus 2. What is the notation VL? I have not remember.
Which one?
VL.
Okay,
X to the power.
VL just denote, okay, VL or F, let's say. This denotes a set of roots of polynomial f in the field L. So this is the definition. This just writes all the roots of polynomial f, or better I should say zeros, because I am just using the polynomial. So zeros of polynomial f in the field L.
Acha.
So at this place, L is the splitting field. So x raised to power p minus 2 in the field L, all the roots should be there, right? So all the roots of the polynomial should be there. So we just write all the roots, and as eta p raised to power, any of these are not equal. So we already have p elements, and we know that this count will definitely be less than the degree of x raised to power p minus 2, which is p, less than or equal to. So this is less than or equal to p, hence it is exactly equal to p, because there could be repetitions. But here we have all these elements. Also, so this implies x raised to power p minus x has all the roots splits into simple linear factors in L. Okay, simple, again, simple means there is no repetition. Roots are every root is repeated once. So is that okay?
Yes.
Okay. Now, yeah. So recall. Okay. So let's see, what do we have? Now we have to. So we have checked what is L. Now we have to see that what is QA eta p. So firstly, L should contain all the roots. So L should be at most this, or if you want, I can write like this: A zeta p, A zeta p raised to power p minus 1. Right? We want all the roots. So we should have something like that. L should be this, because this is a field. This is a rational field. So we have these elements and Q is there. So L should be this. Is that okay?
Okay.
We are not saying these elements like we can have some smaller sets so that it could be generated. That is a different thing. But at least we should have these elements in the set in the field L. So and it should be generated by that, not generated. That means these elements should be there at least, and we should make that a field. So that's why we can use this. Okay, so now let's see. So firstly, since since this by this is equal to what, zeta p, right?
Yes.
Okay, so this implies zeta p belongs to L, because this is there, A is there, A zeta p is there, so zeta p will also be there. So we can write this implies Q A comma zeta p is contained in L, because these are just fewer elements, just A and zeta p. Zeta p we have seen it can be obtained by these two elements. So with the definition of L like this, we should have Q A comma zeta p should be in L. Now we have to prove other way around. So let's see other side. Other side means we should be able to say that L is contained here. So what does this mean? All these elements should be in Q A comma zeta p. And does this look okay? Since,
Yes. Okay.
right, A into zeta p and all the powers, this belongs to Q A comma zeta p. This implies for all k 0 to p minus 1, this implies Q A comma zeta p. L is contained in this, and hence L should be equal to A comma zeta p. So, which was the requirement for the A part. Okay?
Okay.
Okay. Right. I just want to comment one thing. Okay. So So now we have to prove B part. Describe generators of the Galois field G is equal to Galois L over K. If we denote G to be the Galois group L over K with their action on A and zeta P. So what we need to figure out what is the Galois group G, which is Galois L over K.
Yes, Galois group is the uh, group of the automorphism from the extension field to itself,
From the
which fixed
hmm.
which fixes the element of the field base field.
Yeah, and what kind of automorphisms?
Uh, what kind of automorphism? Uh, Linear and ring homomorphism.
Exactly. Yeah. Q algebra automorphisms. Yeah, very good, both of you. So this is exactly K algebra. So K right now we can write Q. Q algebra automorphisms. That is important as we have seen. So automorphism. Yeah, Q algebra automorphism. What does this mean? This means this is a Q linear automorphism, which can be said because L is also a vector space or Q vector space. And second, this is ring homomorphism or isomorphism because this is automorphism. And how it has ring isomorphism, because L has ring structure also. So both of the structure are there. So this is a Q algebra. Yeah, this L is a Q algebra, and we can define automorphisms, Q algebra automorphisms. So this we have. So we have all these properties of linearity and ring isomorphisms. Very good. So we have to find what is this G. Okay. Now L is, we have proved L is equal to Q A zeta. Right. We have just proved in A part by A. So right now we have to define what are all the automorphisms. So automorphism is what? Automorphism is from L to L, and we also say like, okay, what is a typical element of automorphism? Let's say we denote by sigma. Let sigma belongs to automorphism of L, or equivalently we can write this, or G as it is given. Okay, sigma belongs to G. That means if this is given, so what we will try to find, where it maps all the elements of A, right? And what does this mean? Now elements, we already know this is a Q algebra isomorphism. Firstly, it will fix Q for sure because this is a Q algebra isomorphism. So we have all the properties like okay, we can write it out. So if x plus y should be sigma x plus sigma y, and this is C x, this is C sigma x, where C belongs to Q. So this comes from the Q linear isomorphism, Q linear homomorphism for now, let's say. And second, you take x into y, that should map to this sigma y, and there is this condition, identity should map to identity of like 1 of multiplication. So in Q we know that this is 1, so 1 should map to 1, and that is already ensured because this is a Q linear homomorphism, and this comes from the field isomorphism or ring isomorphism. So homomorphism again. Now isomorphism means it should be a bijective map. So we have all these properties, right? So let's see what do we get from here. So from this property, if we put x is equal to 1, then we will get, okay, so this combinedly, if we take C into x, this is C sigma x, since this for all C belongs to Q, only for Q means base field, whatever field we have taken. So this is C into, if I put x is equal to 1, then what we will get this. Now sigma 1 is 1 from this field homomorphism. So this is C. So we obtained that sigma C is equal to C for all C belongs to Q. So it fixes Q. Okay, so Q is fixed. Now if you know that all the elements, so all the elements of Q, A and A zeta, okay, I forget B all the time, sorry about that. So we have this, so we know that Q is fixed. Okay, now if this is fixed, every element will map to itself. Now where A goes, where eta P goes, if you know these two things, can you get all the images, like images of all the elements? Because what is a element, what is a typical element of this looks like? This is something of the kind, some linear combinations of powers of these elements. So for example, it will be like summation a raised to not p, let me write SNT maybe. Okay, something of this kind, and you have some C is some element from Q, and this sum will be finite sum. Okay, and SNT belongs to M union 0. Okay, so any element will look like some linear combinations of powers of A and zeta P. So S could be 0, then it will just become the power of eta P, and there will be some coefficient from Q. So you will have some, any element will look like this. Also we are in finite extension, so we can prove that this is a finite extension, so this is algebraic, so square bracket will be same as this. So we just don't have for the divisors, like for something like fx by gx can also be realized as some polynomial, like like fx by gx can be realized as some polynomial, because we know that these are same. This only contains polynomials, this contains fractions of polynomials. Is that okay?
Please.
Yeah. Okay. So we have, so every element will look like this, and now if every element look like this, then if we want the map, so where will it map? Because firstly we know that over sum it will split because of because of field because of vector space homomorphism, q linear homomorphism. Linear means vector space homomorphism, you know that. So this is summation st, because this is finite sum, you can induct, and so this is for just 2 x and y, then you can apply induction and get for any finite sequence. So you have this, sorry, sigma of c a raised to power s zeta p raised to power t. Now this is s comma t. Now you know that in the product we can apply the ring homomorphism, and it will just split as sigma c sigma a raised to power s, and we can further split as some power of this. You have this. Now you know that sigma c is just c. Again, these are all finite sum. Okay, so sigma a raised to power s and sigma zeta p raised to power t. So what is the upshot of this? We just need where a is mapping and where zeta p is mapping. So we just, if we know the information over generators, we can get the value for every element. Okay, we know where q is mapping, we just need to find where a and zeta p is mapping. Okay, so it is enough to get information for sigma of like a and zeta p, where these elements are mapping. So let's see. Okay, so Okay. So sigma belongs to, as I said, G, which is the
Ma'am, please
yeah.
please scroll down once.
Yeah.
Okay.
Now I've started uploading these live session notes also. So
Ach-
yeah,
oh,
that will be helpful for you. I'm just putting it up directly.
okay, ma'am. Here, what you did? See, this formation, right? Sigma of general element of the
Mm-hmm.
Q,
Mm-hmm.
finite.
Finite
Then
sum, yeah. Hmm. We
uh,
we don't have infinite sum in terms
um,
of this field, yeah.
take. Okay, okay.
Because this is the notation for polynomial, so we never have infinite sum. Infinite sum comes in formal power series, if you know. So there is this notation for that, double bracket.
Uh,
And that is
uh,
different. This is just set of polynomials, and polynomials is a finite sum of these monomials, you can say.
okay. Here, mu p is algebraic, so two types are equal. Quotient field and uh, square bracket and open bracket.
Yeah, this is always the case. If it is algebraic, then so why this happens is if you remember, because we have so what does this look like? What is 1 by a? We know
Mm.
that so a raised to power something, like let's say p min okay, whatever. Since a is algebraic, you will have some polynomial corresponding to it. So f a will be 0 for some non-zero polynomial f, right, if it is algebraic.
Yes.
So if a is algebraic, then we have this situation, we have this condition now. So for some polynomial f, we have this. Now 1 by a, so this is something you need to write it rigorously. But for example, okay, so this a, so what you need to find, what is a inverse. So you have some polynomial, let's say a raised to power n minus something something is equal to 0, right? So what you can do, just so, I just write, let's say this is of degree, okay, never mind. So we just take d, okay, d1 a raised to power n minus 1, and you get dn, okay. So you just take this outside, so you just say this is non-zero, so you can write like this, like coefficient of a raised to power n, you will get something something, and dn minus 1 plus dn is equal to 0. So what you really get, so you can write minus dn by a, then you will get something like this. And you can divide dn. Firstly, you just find what is non-zero, so last non-zero one. So I'll take common that element. So what I mean to say, so if you have if this is a minimal polynomial, this will look like that, because you cannot have something like a into something full, right? So dn will be non-zero. If it is non-zero, we can go back to the previous element, but if we are talking just about minimal polynomial, then this is fine, right? Because we are in fields. So if you have minimal polynomial of the kind like f is equal to a into g, where a is that element for which f is a minimal polynomial, then we can also consider g, right? Because this is an integral domain, we cannot have product of two elements to be 0, one of them has to be 0. Since a is non-zero, so g has to be 0, right?
Okay, right.
Yeah, so dn cannot be 0. So now you will get this dn minus 1 by minus dn. So 1 by a, you can write 1 by a as this. So that is a polynomial. Okay, so whenever you have some polynomial dividing it, so if you have something like this, then you can write it as some hx. Okay, so that's what, so if this is algebraic, so inverse can be written as some kind of a polynomial. So that's why we can say that this square bracket is same as small brackets functional field. Okay, and
Okay.
why I'm saying this is algebraic, because this is a finite extension. This we will prove it, what is the degree of this extension, but at least you have seen a has some polynomial, like which it satisfies, or you can at least say this is a splitting field of the polynomial this. So we will prove that this is finite. So this is finite, so that means it is algebraic, and since this is algebraic, all the elements of this fraction we can write it in terms of a polynomial. Okay, is that okay? Okay,
Yes, okay.
yeah, okay. So we have so what do we have? If we take some sigma in G, which is the Galois group of q a comma eta p, then sigma can be defined by uh, I don't know, knowledge of uh, where a and zeta p map. Okay, where these elements map, we can get it from like this information is enough to get the information of sigma. So let's see what are the options for this. Do we know something for that? Again, for Q algebra isomorphisms. Okay, I can just make it big. Do we know anything? Like, can we restrict where A will map? Like, it cannot map to any element. So, firstly, it cannot map to Q. Okay? This cannot be. Why am I saying that? This is a isomorphism. Cannot be Q, because this is a isomorphism, and since Q sigma fixes Q, so every element is already mapped in Q, like, because elements of Q will map to itself, so every element of Q is mapped already, so we cannot have that option for isomorphism. So A should not be an element of Q. A should not map to any element of Q. But we have one condition, if you remember from the notes. So we have this, we can also prove if, so if,
Ma'am,
yeah,
maybe irrational. So, because here A cannot map into Q because this is a isomorphism.
mm-hmm.
Q fixes Q. Oh, haha, yes, yes. Tick, tick.
Q fixes Q, so it cannot
Ah,
map to
okay.
Q, because this does not belong to Q also, like we have already seen. If it belongs to Q, then we don't have that extension. And A is like A raised to power P is equal to 2, and this is Pth root, so Q does not contain that, because as we know we cannot write it as some Q by R, where R is non-zero, right? So that's why we have this condition. Now let's see. So there is one more thing we can use. If A is a root of some polynomial some polynomial, we don't care which it is. So some polynomial g in qx. In qx is important, right? I'll explain why. In qx, then sigma of a, this same sigma of a will be sigma of a is also a root of same polynomial g, or is also a root of g. Can you see it? So let's see what do we mean by that. So a is a root of some polynomial g, that means g of a should be 0, right? So a is a root, given information is ga is equal to 0, okay, and coefficients of g are coming from q. So ga is 0. Now let's apply sigma of ga. Then what will be sigma of ga? Since ga is 0, so this will be 0. And you know that 0 will map to 0 because q is fixed. Elements of q are fixed. Q belongs to q, so sigma of 0 should be 0. So one side we have this. And now let's see, as we have seen, this is a polynomial, right? This is a polynomial in q. So this is very important. This is a polynomial in q. That means it is like something, okay, I can write like this. We have already seen. So, or if you want to write, yeah, it's fine. Okay, g n a raised to power n. Let's say this. Okay, we don't know what is the degree of g. Let's say this is n, and so g is a polynomial, and when you put a, just replace x by a. So we have this. Now since these coefficients are in q, so that means and you know that, so this is so by this property means sigma, linearity, q linearity of sigma, because this is a linear isomorphism. We can write it like this: sigma of g1a, and not even g1a, we can also write g1 sigma of a, because g1 belongs to q, and we have this property, this one. So c belongs to q, so you know that if this is a linear homomorphism and this is q linear, so any element of q appears, then it does not do anything at q. So c into sigma x. Okay, so we will get this, and up to and so on, g n sigma a raised to power n. And now second thing, we have this. And also we know that sigma, what sigma does on elements of q, this just fix it. So you'll get this, and again this is this. Now what does it do at this sigma of a raised to power n? So it is like a into a into a, and by the ring homomorphism, we have sigma of a raised to power n, because if sigma of x into y is same as sigma of x into sigma of y, and since x and y are same, so it's just sigma of x square, that will be sigma x square. So you will get, this is, you can write as summation, or much better we can write it to be so it's just, this is the same polynomial, as you can see, same polynomial, but at the place of a, it has now become sigma of a. So this is this. So it can interchange sigma and g. Is that okay?
Yeah. Yes.
Okay, great. So this is all happening because this is a Q algebra homomorphism. We have not used even isomorphism. So we have this condition. This is equal to, now so since sigma of GA, since sigma of GA is equal to 0, this implies, as we have seen, sigma of GA is same as G of sigma A. So this is also 0. And what does this mean? This implies sigma is also a root of g of x of the polynomial g. So it is also a root of g. I don't need to write even x, I can just say root of g. Firstly, this is happening because coefficients are from Q. You cannot take coefficients from the bigger field or something. We have to stick to Q because this is a Q algebra isomorphism. That is important. So this is statement, so maybe if you want to write lemma. Okay, so we have this. So in the light of this lemma, we know that A should map to some root of the polynomial, not the polynomial. We can say a polynomial which has the root A. Okay, so A should map to. So you consider a polynomial of which A is a root, and then you can map it to some other root of the same polynomial. That is one option. Okay, now there is one more condition. It should map to same like, okay, so what I mean to say, okay, we don't have all that options, like, okay, let me, okay, so A should map to somewhere, zeta p should map to somewhere. So firstly, I am claiming that it should be a minimal polynomial of it. Why I'm saying that? So you have to consider this f to be a minimal polynomial of it, because so we have proved one thing, that sigma of A is a root of polynomial g. Okay, sigma of A should be a root of polynomial g if, okay, A is a, in notationally we have proved that g is equal to 0. This implies sigma of g of sigma is equal to 0. Okay, so sigma of A should be a root of the same polynomial. Now we have proved one side. Now we have to pick the roots from this. Okay, roots from sigma A. Okay, we don't have all the choices. All the choices means, okay, let me explain like that. Okay, we need to find what are all the options for sigma A. That is our task, right? Because we need to find sigma, that we have seen that it can be obtained from A and zeta p. Okay, so now, for example, if G can be written as f into h, okay, then so it should be the root of one of these factors, right? So this implies either f of A is equal to 0 or h of A is equal to 0. Okay, this implies, now if you have considered, for example, okay, so my point is, for example, let's say A is a root of, now let fa is equal to 0 and ha is not equal to 0. This could happen, like if you can factor it out, and it is a root of one of the factors from f, not from g, not from h. Okay, so that means we cannot take any, so sigma, what are all the choices for sigma A here? We cannot take sigma A if you have started with G, and for example you have mapped A to some root of H which is not a root of F. So if sigma of A, if you apply F, this is non-zero and H of sigma A is equal to 0, then we cannot consider this case. Do you getting my point? So I am saying you start with G, okay, Now if g is such that you have we have one side like g of a is equal to 0, then g of sigma a is equal to 0. But what are all the choices of sigma a you can consider? That's it, that is our question. So if we consider g, and g can be factored in f and h again in qx, like these are not happening in the bigger field, just f and h are still in qx. So for example, you have x square minus 4. Okay, then you can factor it as x minus 2 and x plus 2. So this is for example your g. And if you have taken g of 2, like let, okay, this is not a good example here because 2 is already in q, but
root 2 and 2 root 2 and root 2 x square minus 2 into x square minus 3.
x square minus 2 and x square minus plus 2.
Yes, ma'am.
Oh, yeah.
No, ma'am. I'm saying for the other example, if you take x square minus 2 into x square minus 3.
Minus 3.
So root 2, yes.
Yeah, okay, right, exactly. Very good. Yeah, so you consider this example g to be this, then and let a is equal to root 2. Yeah, this example definitely work. Nice. So you have a is
And
yeah.
And ma'am, also we prove it by if G is equal to f of h, and if we are saying that a sigma of a map to be b, where b is not a root of a f. So we prove above sigma of f of a is same as the f of a sigma a. So
Exactly.
one side we get a 0 and other side f of b which is not 0.
Exactly. Yeah, at this step we should, so this is exactly why we get a contradiction. So contradiction to this lemma itself, because f of sigma is non-zero, it is turning out to be this. So yeah, so for example in this case, g, if g is this and if a is this and sigma of a you pick it to be root 3, then you will get a this is not okay. Why? Because root 2 is a root of this factor and root 3 is a root of this factor. So this factors itself, if you consider f, exactly f in your lemma, then f of a, that is f of root 2 is 0, then f of sigma a should also be 0. So because of this you should have irreducible polynomial. So this condition is you can even modify some irreducible polynomial. So I'll change the color, some irreducible polynomial. Okay, and then it becomes if and only if. So sigma of a is also a root if it is a irreducible polynomial. So we have to follow this. So this implies what we get in turn, sigma, if we want to define this, so where a is mapping and where zeta p is mapping. So the choice for a, we have all the roots. So what we can do, we are talking about irreducible polynomial, we can talk about minimal polynomial, we just take it to be monic. And so you consider roots of, so a sigma of a could be anything among roots of the minimal polynomial of a. So you pick the minimal polynomial and then you allow sigma a to be among those options. Similarly, zeta p has the same property. Okay, this is for any general element, even for q also, because you know that if any element is q, like if the polynomial, so that is just a linear polynomial, you take x minus a, then the choice for, so what are all the roots of x minus a, that are a. So again, what are all the where the roots we are looking at the roots in L, we don't have other options, right? the root should be from L, because these are the elements from L, the field which are taking the extension field we are considering. Okay, very good. So so let's see what is the minimal polynomial of A. Of A over Q. Of course, we are only talking about over Q. So what is the minimal polynomial? We already have it, right? So what is the condition? So we are saying, you know that A raised to power P is equal to 2. So for minimal polynomial we have that condition. So this is x raised to power P minus 2, right? So this is the minimal polynomial. Also, if you want to, yeah, any doubts? Yeah, in QX Q. So for minimal polynomial, what do you have in terms of the options? So a raised to power P is equal to 2. So that is okay, that is some polynomial of which A is a root. Then can you have some lesser degree polynomials? So if you take mu of A in Q, can you find something? That is our next question, right? So can you find a factor of this? But any factor will contain some power of A, that you can prove, because any less degree power of A, then we'll not get it, because and this is pth root of 2. So you can argue like this. Okay, so this is a minimal polynomial of A over Q. Now yeah, so let's see what do we have now. So A can map to roots of A raised to power P or x raised to power P minus 2. Okay, roots of which is the set like A zeta square. Okay, pth. We have already seen these are all the roots. Okay.
Okay.
Okay. So these are all the options. Now let's see where zeta will map. What is the minimal polynomial of zeta? That we already know. This is, yeah, tell me, what is the minimal polynomial of zeta?
What is the
So we have, yeah,
Ma'am,
yeah.
x to the power p minus 1 plus x to the power p minus 2 and so on plus x plus 1
X raised to power P minus 1, and then
plus x to the power
hmm,
minus 1 is in the power.
uh, okay, let me write it down. So can you come again? So X raised to power
P minus 1
hmm,
plus x to the power p minus 2 and so on plus x plus 1.
exactly. So this is how this is coming. So if you know, in the lectures we have this, like minimal polynomial is zeta is phi x. This is the minimal polynomial of so this is actually in general zeta n x is the minimal polynomial of zeta n. Okay, and what is this? This by definition is all the x minus zeta. Now this zeta is different, or maybe you can write zeta n. Okay, let me write alpha only, will not get confused. So where alpha raised to power n is equal to 1, and GCD of, oh okay, yeah, order of alpha is equal to m. So what does this mean? You take all the powers, let's say I can write zeta n now, and you take powers r, where zeta n is raised to power n is equal to 1, and order of, sorry, no, order of again zeta n is but r has some condition, r and n should be 1, like GCD of r and n should be 1. So this is basically the product of all the generators, all the primitive elements, for which if you do the powers you get all the units, roots of unit, nth roots of unity. So that is the definition. Okay, that is proved in the lectures, so we just stick to that. Okay, so we have this, and in the case of in our case n is given to be p, so we have some restriction means, so we have phi, so this implies phi p of x is what, you take zeta n raised to power n is equal to 1, so this is p, and you have GCD of p comma n is equal to 1, sorry, r comma p is equal to 1. But if you remember, and there is a condition on r that I should also write. R is in between 0 to not 0 actually. Actually 0 will never come, so that's okay. So 1 to n. Okay, so we have this, and again you have 1 is less than or equal to this. Now r and p, the GCD of r and p will always be 1, because if r is not a element, okay, I should go till n minus 1. So this is always the, r, if r is in between 1 to p minus 1, the GCD with p will always be 1. So we have all the factors like zeta n, zeta n square, you go up to zeta n, so this is p minus 1. So that means so this is a normal product. Actually you can write it like x raised to power p. So actually this is all the roots of p, so that is x raised to power p minus 1, divided by, you just divide by x minus 1, because 1 is also a root, but it will not appear in phi p. So this is so x raised to power p minus 1 can be factored as in linear factors with using all the roots of unity. So we have all the factors. Now 1 is also there, but other roots are the generators, because we have everything like zp star, this is isomorphic to yeah, zeros of x raised to power p minus 1. So this is like we have everything for this. So this is exactly equal to as yeah, Anjani said, x raised to power p minus 1 plus up to and so on. This is 1. Yeah, you know how it divides it. We just get the factor x raised to power p minus 1 plus x raised to power p minus 2 up to and so on plus 1. So this is the thing. Okay, that's why phi n x will be this. So main thing is so this implies zeta will map to some zeta raised to power k, where k is in between so roots of minimal polynomial, that is these p minus 1. So you have 1 to p minus 1. So degree of phi px is equal to p minus 1. As you have seen, there is just one element missing, which is x minus 1. That factor we are not considering, because 1 so from the definition itself it is not there. Is that okay?
Yes.
Okay, so very good. So we have sigma, which is defined by two things, which is A and zeta, and we have obtained where it could map. So in general, what I can write, this is zeta k, and I can write this will map to A zeta, sorry, not k here. So I always forget p. This is p, zeta p raised to power k, and you have zeta p raised to power s, where k is in between 1 to p minus 1, and where s can map where s from where s could be there, like, so we have all options as all the roots of the minimal polynomial x raised to power p minus a. So you can write it in general as, what are all the roots? A zeta p, a zeta p square, a zeta p raised to power p minus 1. These are all the options we have. So we can have s to be 0, which will give a. We can have s to be 1, which will give a zeta p, and up to and so on. S is equal to p minus 1. So s can map from 0 to p minus 1. So these are all the options we have. Okay. So in total, what do we have? This implies automorphism group of sorry, of L okay, Q algebra isomorphisms of L, which is Q A comma zeta P, that is your G. The cardinality of this is equal to P into P minus 1. I am saying P into P minus 1 because options are K is going from 1 to P minus 1 and S is going from 0 to P minus 1. So S has P options and K has P minus 1 options. So in total we have P into P minus 1 options for A and zeta P to map it to. So we have this. Okay.
Ma'am, I am not getting the point. Last line.
Mm-hmm. So this is okay. So every automorphism is defined by where these two elements map. Okay.
Okay. Hmm.
Now, what are all the options for A and zeta p? We have obtained A could map to A zeta p raised to power s, and zeta p could map to
Oh,
zeta p.
yes, understand. I mean, how many ways we can choose zeta p and uh,
Yeah, how
both
many
both.
ways we can choose this element and this element?
So,
That is dependent
and
on K and S. So, how
okay,
many
okay,
options? Yeah.
okay, okay, fine, fine.
Okay, great. So we have this cardinality. Now, okay, so this is one thing. Now we will also prove. So in the question it was asked, what is the Galois group? So that we have found. Okay, describe generators of the Galois group with their action on A and zeta p. So we have already seen what are all the actions on A and zeta p it could have, how it can be, it can act. So action is basically what you have this natural. Uh, so you have uh, G cross L to this. So sigma comma x will map to sigma of x. So this is the action. Okay. Yeah. So that's why it is asking. So where it is mapping A and zeta p, that will define the Galois group. Uh, okay. Typical element of Galois group. Okay. So we have this. Now let's go to the point C. Used to establish the canonical isomorphism of G onto the affine group this. Actually, we have all the things for this C part. So what does C part say? So okay, I'll write this down. Hmm. So let's move to the C part, which says firstly what is affine line. Affine line of FP is all those ux plus v such that u belongs to fp star and v belongs to fp. So this is, by definition we have this. Okay, this is a fine line of fp. Now okay, so now what do we have? so x is some variable. So okay, so a fine line of fp is just a finite field. So in real, so a1 of r is basically what, this is just your real line. Okay, so if you know some geometry, this affine, when we say this, there is no element like 0 0 or something. It's just a set of uh, a set of real numbers, just that. There is no special element like 0 0. So basically there is no so like there is nothing like it has some topology or it has some group structure. So there is no structure on R. It's just that, it's just a collection of some numbers. So similarly in finite set we have this. Okay, so now let's see what we have been asked. So you have to find a group isomorphism. So this forms a group under composition. So under composition means, so x is some variable, just think of it as like this. So so this is a group, a fine group. So this is general linear group, kind of a fine group, and this can be seen as so any element of, let's say this. So you have the composition. So composition is like a function. Okay, so you can think of it as where x is mapping, this is mapping it to this, and here x is mapping it to u2 x plus v1, u2 x plus v2. So operation will be like, when you compose it, what will you do? You will replace x to the other element. So it's like you are operating on this. So you will get this element as u2x plus v2 plus v1. So you have this composition. So composition of functions, like, okay, composition of these two functions. So you will get u1 u2 into x plus u1 v2 plus v1. So you have this element. Note that this is again non-zero. Non-zero means this is from fp star, because if u1 is from fp star and u2 is from fp star, then u1 u2 will also be, because this fp is a field, so it cannot have product to be 0, because this is an integral domain. So you have this, and this is also in fp, so this also belongs to a1 fp. So this is a group under composition. So you can prove inverse and everything. So you have this. Now so you have been asked, just map this to this. So define, so there's a canonical isomorphism. Why we are saying canonical isomorphism? We have two things. Earlier we have just seen where A is mapping to zeta p raised to power s, and zeta p is mapping to zeta p raised to power k. Any sigma is like this. So this will map to under this canonical isomorphism. So we have to prove that there is a canonical isomorphism between these. So how we are defining? Any element will map to so any element of a1 fp look like ux plus v. Okay, so what is varying here? S and k are varying, and we have this condition that s should be from 0 to p minus 1, and k should be from 1 to p minus 1. We have seen that that's what we did, because k cannot be 0, because it should be a root of minimal polynomial of zeta p, and that is without this x minus 1 factor. Okay, because if k is 0, that will be 1, so we don't have it as a in the minimal part. Okay, so that factor we don't have. So as you can see, k can go from 1 to p minus 1, so it is like zp cross. Okay, so what we can define it to be k into x plus s, right? Then it will belong to a1 fp. Why? Because a1 fp is like ux plus v, where u belongs to fp star and v belongs to fp. Is the map okay? Is the map okay? I can explain again if you have any doubt.
Yes, I'm seeing.
Is that okay? So we just see where A and zeta p is mapping. That defines what is sigma, and where we will map sigma to b. Sigma will map it to what is the what is k and s in this map. So we have this unique. So this is definitely a function. So we don't have any problem here because zeta p raised to power k is not same as zeta p raised to power k dash if k is not equal to k dash. Of course, k is in between 1 to p minus 1. So mod
Ma'am,
p, yeah.
sigma sending the element A zeta p to
Hmm.
the kx plus s,
Hmm.
which is element of the affine group.
Hmm.
Uh,
Right.
but how look like the body of the function? I
So
mean
so function,
sigma.
okay. So function is like g is a1 to fp. So you pick sigma first, okay? So where sigma is mapping, okay?
Mm,
So you write
yes.
it to be kx plus s, where
Mm,
k and s are such that sigma of a is equal to a zeta p raised to power s, and sigma of zeta p is equal to zeta p raised to power k. Is that okay?
oh, okay,
We can
okay.
write like this, okay, because sigma is
Mm,
defined with these two elements independently. It's not like there is any clash means it's not like if you define a, you cannot independently define zeta p. It's not the case. These are separate generators. Like it does not affect any map of a and zeta p does not affect each other. That's important. Otherwise we don't have choices. Like we, at this point we have all the choices for a and zeta p separately. So this is the
okay.
map. Yeah. And this is well and good in A1 FP because we know that K cannot be 0, and K and S are mod P, like it's just going from 0, S is going from 0 to P minus 1, and K is going from 1 to K, 1 to P minus 1. So we are good. Okay. Now this is the canonical map. We don't know if this is a homomorphism or not, but at least you can also see that this is a bijective map, because if you pick any element on the right hand side you can get a element for sigma, because whatever k and s you get, you just define sigma to be sigma of a goes to a zeta p raised to power s, and sigma of zeta p is equal to zeta p raised to power k. As I said, the choice for a and zeta p does not depend on each other, so we have no problem in terms of like s has some limits or k has some limits. That is not the case. So this is bijective also. So we just need to prove that this is a homomorphism, because this is a group, this is a group. So we can say that this is a group homomorphism in good situations. So let's see if this is a homomorphism. So we are talking about a map from here to here. So let's say this is psi. Okay. So psi of G1, or maybe let's say sigma 1 of sigma 2. So these are groups, and this automorphism group again, it is a function group. So we have this composition. Usually we just take composition and we have this operation. Sigma 1 of sigma 2. What will it be? So what is sigma 1 of sigma 2? That is, okay, let's see what does this be. So let me write like this. Let sigma 1 and sigma 2 belongs to G, such that, or maybe defined by, I guess enough, we can just define by sigma 1 of A is equal to A zeta P. I'll write S1, and sigma 1 of zeta p is equal to zeta p raised to power k1, and sigma 2 of a is equal to a into zeta p raised to power s2, and zeta sigma 2 a zeta p raised to power k1 k2. Okay, so we have this. So now what is sigma 1 of sigma 2? Because what we need to show, so for group homomorphism, what do we need to show? Psi of sigma 1 of sigma 2 should be equal to this of, because that is also a fine group. So we have under composition, as we wrote earlier. So this we need to prove. Okay, and note that this and okay, yeah, identity goes to identity of this, so that is fine. Because okay, what is identity? Identity means a goes to a, and zeta p goes to zeta p. Okay, it maps to itself. That is this implies so what is a so we are mapping using k and s. Okay, so what does this mean? A maps to a, that means s1 is 0, not s1, s is 0, and k is, so k is what? K is the power of zeta p, that is 1. So this should map to where? This should map to as we wrote 1 into x plus 0, that is x. So as I said, for affine group is also a function set of functions. Okay, so we again have composition, and the identity element is the map, identity map, that is x goes to x, that is identity. You can check. So yeah, x goes to x. Okay, so this is the identity. Okay, yeah, or you just think as we have written like this. So this is just think of any two element will map to the composition. So when it will be the same where we started, what I mean to say, yeah, so u1 so yeah, you can check, this is the identity element of identity of a1 fp. Actually, this can be seen directly with the function. You can also see from here. Okay. Okay, so this is the case. So we just need to see what is sigma 1 of sigma 2. So what is this? Sigma 1 of sigma 2. Now we know where it is mapping. So sigma 2 is what? Sigma 2 is mapping a to a zeta p raised to power s. So what we need to find? So we need to find two things. Zeta 1 of zeta 2 of a. So sigma 1, sigma 2, sigma of this. What is sigma 2a? Sigma 2a we just have seen, that is equal to zeta p raised to power k2. And then now where k zeta p raised to power k go? This is zeta 1 raised to power because we know that this is a Q algebra homomorphism. So we have this, and sigma 1 of a is equal to a zeta p raised to power what is the notation? K s1, and this will be now we can go like k2, we can make it in power. So I'll just write again, because this is again a K algebra homomorphism. So sigma 1 of zeta p is equal to zeta p raised to power k1, and this is power k2. Or have I written wrong? Oh, this is s2. I'm just using what are where sigma 1 and sigma 2 mapping the elements a and zeta p. So I'm just doing that thing. So this is S2. So you actually get zeta p raised to power S1 plus K1 S2. And from the other side also you will get same. Other side means, sorry, what is zeta sigma 1, yeah, what, so this implies yeah, so you also need to find what is this, because the map psi of any element will be defined by using what is the map for A and zeta p. So for example, this we know that, so this is kx plus s. So s we got, s is equal to s1 plus k1 s2. We already get this. Now we need to find what is this. This comes from zeta, the map of zeta p. So zeta, where zeta p is mapping, so zeta p is mapping to, so yeah, so zeta p,
zeta to the power t k1.
yeah, so you get here k2 and zeta p raised to power k1 k2, right?
This one.
Yeah, exactly. Very good. So you get this. So this is the map. Now what you need to see, what is this? So psi of sigma 1 we already have seen, that is so k1 x plus s1 of k2 x plus s2. So of means you will replace x by this element, composition. So you get k1 k2 x plus k1 s2 plus s1. This is exactly the same way as this. So this is indeed a homomorphism. So psi is the canonical isomorphism group isomorphism, if you want to write. Both are groups, okay? Right, so we have proved this. So now there is most important thing of this, that fourth part is asking for, okay, let's see, what does this ask? Okay, yeah. So draw the diagrams of the lattice of intermediate fields of L over Q and the lattice of subgroups G indicating the various containments. Which intermediate fields of L over Q are Galois over Q? So basically, so you have seen from fundamental theorem of Galois theory that we have one-to-one correspondence between uh, between fields, intermediate fields of L over Q and subgroups of G. Okay, subgroups of G means G is the Galois group of L over Q. When does this happen? When it is a Galois extension, right? So we have to see whether this is a Galois extension or not. If not, then of course we don't have much hands on for this question. But if it is, if turns out it to be a Galois extension, then we have this. If you just consider a group, then corresponding subgroup. We have the map also. We know how, if we have a subgroup, then we can get back to the intermediate fields using what, using using fixed fields, right? We have that map, we did it last time also. So firstly we should check what, so it looks like this should be a Galois extension, but we have to prove that. So okay, so for Galois extension, what is the requirement? Can you tell me, is L over Q Galois extension? So L is your Q A zeta P. Okay, what is the requirement? You know there's so what is the definition, basic definition for Galois extension? Do you remember?
Uh,
Yeah.
Order of the Galois group is
Hmm.
the equal to the extension of the field L over Q.
Exactly, very good. So, if this is the case, you know that this is always the case. This is always less than or equal to L over Q. But when this happens, if this, then L is said to be Galois extension of Q. Okay, so let's try to do that. We already have L over Q. What is this? I mean the cardinality, of course.
Ma'am, I have not understand the question for what it is saying.
Okay, so question 4 part is saying so there is L, there is Q. Okay, so there are intermediate fields, right? There is some field, we don't know, maybe Q
Yes.
something. So there are some intermediate fields. So for example, if you have root 2 comma root 3, we did it last time. So it's like you have Q root 2, you have Q root 3. You could
Curate
have
6.
so many, like we don't know root 2 plus root 3. That is not actually comes here, but yeah, we don't know. There could be multiplication, there could be so many subfields even generated by 3 elements. Or so question is asking, you have this class of intermediate fields, and there is this class of G, Galois group G, and identity. So you have this, so identity means subgroup, I mean. So the other side you have subgroups of G. Okay, so question is asking, just write, define or give a classification of all the subgroups of G, and so you find all the lattice for intermediate subfields and subgroups of G. So the question is asking that, but I'm saying, when do you have hands on this question? Like you have, from fundamental theorem of Galois theory, you know one thing, that if L is a Galois extension, then every subgroup of G gives a intermediate field, and intermediate field gives a subgroup of G. So there is a one-to-one correspondence. For every subgroup we have like for each subgroup we have a unique intermediate field. That's the thing we know from fundamental theorem of Galois theory. That's really relates subgroups and intermediate subfields. So I'm saying, then only we have some conditions, like otherwise finding subfields it's very hard, because you can have anything like Q root 2 comma, let's say, I don't know, like you just take here, this is a simpler example, but for A and zeta P it's like too much. You can have root 2 plus 2 root 3, or maybe you can have multiple elements. There could be many subfields in between, and even infinite subfields, we don't know that. But if we know the subgroups of G, maybe we can have, so we then we can have intermediate subfields. Okay, but that relation we have only when L is a Galois extension. So if it is not, then there will be a problem, like we don't know, at least we can do that, but we don't know, we have to try many things. But if it is a Galois extension, then we are in a good situation. So that's why I'm saying, let's check if it is a Galois extension or not. Okay.
Okay.
Okay, so let's see. So so what do we need to prove? Cardinality of Galois group of L over Q is same as same as the vector space degree of L over Q, like vector space dimension of L over Q. So we already have seen this cardinality of Galois L over Q, that is equal to what? P into P minus 1. So because you know A can map to this, the number of options, like So you have p raised to power k, sorry, not, this is s is going from 0 to p minus 1, and zeta is going from zeta raised to power t, this is 1 to, so we have calculated this. So there are p options, and in second case we have p minus 1 options. So as we have seen, we just take the product p into p minus 2 because these are independent to each other, and this defines a typical element of a Galois group. So we have this cardinality. Now if we can prove that the vector space dimension of L over Q uh, is exactly p into p minus 1, then we are done. So let's try to do that. So you have Q a comma zeta p over Q. So you have there are at least two options to go to this. So whether you can go via this or you can go via this, right? At least two options are there. What I mean to go via this, because I'm going to write like this. So q a into q zeta p into q. Okay, or I can, okay, why I'm doing, oh okay, I mixed up. So q a, whether I can go by this multiplication q a over q, or you can take q a comma zeta p q q a comma zeta p q zeta p q zeta p q. Okay, so let's see what do we know, because the point is the hard part is finding either this or this, because base field is q zeta p and here base field is q a, so we don't know how much degree it could have. Okay, so that's why I wrote both. We might have to use both of these equalities. Okay, so let's try to find, firstly let's see what do we know about this. So what is qa over q? Do you know? So as we have already seen, so this is a simple extension. Okay, so for such a simple extension, what do we know? If we know degree of minimal polynomial, then we are done. So we have already seen what is the minimal polynomial of element a over q, that is x raised to power p minus a. Oh yeah, also we can see directly this is a minimal this is the minimal polynomial. Earlier I said you can check it, but so one option is definitely this, right? Yeah, so one option is definitely x raised to power p minus a, because a satisfies this equation. Now we have to check that if this is a minimal polynomial. Okay, so can you tell me how can you check? So can you use Eisenstein criterion? Oh sorry, this is not a, this is 2, right? So a is a root of this polynomial x raised to power p minus 2, right? So I am trying to find this. What is this? So a satisfies, so this is so we know that this is equal to degree of minimal polynomial that we have done plenty of times, mu a comma this. So minimal polynomial of a over q. A we know that a satisfies x raised to power p minus 2, that we have from the given condition that a raised to power p is equal to 2. Now we have to check that this is also minimal polynomial, right? So for minimal polynomial, what will you do? So this is a minimal x raised to power p minus 2 is a minimal polynomial. So, for minimal polynomial, you can use Eisenstein criterion. By Eisenstein criterion, what does this say? Eisenstein, yeah. Can you recall? What is Eisenstein criterion for a polynomial? To check whether it is irreducible or not. We can do it over Q only, like Eisenstein criterion is for over Q. We cannot say over Q zeta p or not, but we can of course say over Q. We are only in this condition. So what does this say? You pick two. You pick any prime. So let's take prime to be the element 2. Okay. Then 2 divides a0 and 2 divides ai for all. Okay, I can write it in general. So 2 divides ai for all. So I mean in general, a n x raised to power n up to and so on a0. Okay. So what does this say? 2 should divide ai for all i's from 1 to n. Okay. And oh wait n minus 1. Okay. And
from 0.
yeah, right, it should be 0. Yeah, thank you. So 2 should divide ai from for all I from 0 to n minus 1, and 2 square does not divide a0 and 2 does not divide an. That's these all the conditions requires for saying that this is a irreducible polynomial, right? So let's see if this follows here or not. So 2 divides ai for all I except an, because an is 1 and all the other elements in between are just 0, coefficients are 0. So 2 divides those 0, 2 divides 0, so we are good. And now 2 divides a0, that is also okay. Now 2 square does not divide a0, this is also fine, this is fine, and 2 does not divide an, that is also fine. So what do we have? So x raised to power p minus 2 is irreducible and hence minimal for a in q, in the field q. Is that okay? Are you with me?
Okay.
Yes, ma'am.
Okay, great. So we have, so thus qa over q, this is exactly p, that is the degree of minimal polynomial. Okay, so that's great. Now so as I said, this is p, so this is given to be now we get yeah, this is p. Okay. Now let's see in other inequality. So in this one, so as I said, this first part we are still doubtful, but at least let's see what will be the degree of this. Again, we have already seen minimal polynomial of zeta p. So what will it be? What was the degree? Exactly. Very good. Yeah, very good. So this is p minus 1. So that is also fine. Now observe that in this part. Okay, in this part. So q a comma zeta p over q zeta p. So we have so this is like q. So you have q zeta p. This is your base field. Let's say k, and this is like q a. Sorry, q zeta p and a. So you can write it to be ka. So this is still simple extension. So if we again can find the minimal polynomial of a, then we are done. right, for this extension. So this is again a simple extension, means generated, there is a primitive element, right? So k k ka over k, we just try to find what is the extension degree. That is again come from the minimal polynomial, and that is what is can we give at least one polynomial where which a satisfies? Because whether maybe we cannot find minimal polynomial, but we can at least find one polynomial for which a is a root. So that is what x raised to power p minus a. Again you take the same polynomial, you know that sorry 2, I always write a. So x raised to power p minus 2, you know that a raised to power p is equal to 2. So a has so what I mean to say, I'll change one more color. So you have ka over k, that is something we try to find. So we have one option, we have find a polynomial which a satisfies, whose coefficients are coming from k, that is you can consider it to be x raised to power p minus 2, right? Because coefficient is just 2 and 1, that is definitely in k, because k contains q. So coefficients are coming from k, and a satisfies this polynomial. So that means minimal polynomial must be some degree which is less than or equal to p. So that means what I mean to say, this is definitely less than or equal to p, because we have one polynomial at least which has degree p. So minimal polynomial should have degree less than that. So do you agree for this part? Do you agree?
We have find that the k is to k. This is should be degree of the minimal polynomial of a
Yeah, right.
here.
Hmm.
So
Over
so
k, yeah. Hmm.
so then is equal to be exactly p.
We
It,
don't know that, because what is the problem? Uh, k is actually q zeta p, so maybe some zeta p power can minimize it, we don't know that. Eisenstein criterion only works over q, like if the coefficients not coefficients, if the field is base field is q zeta p. So what Eisenstein criterion says, this x is to power p minus 2 is irreducible in qx,
mm,
but we don't know if it is irreducible in q zeta px. Field
okay.
is little bit bigger, so there might be a possibility that it splits. There is one factor which becomes a problem, like it could reduce it to p minus 2, we don't know that. Okay, but at the end it will become just p, but right now we don't know that. So
Okay.
we just have the information it will be less than or equal to p, that we are sure of. So now, so what do we have? I'll just copy this part, because this is something I need space for that. So we have this. So yeah. So we got this much information. So I'll just use. Um, yeah. So we have this. So how? What information? Yeah.
Here you have underlined those. It is divided by
No, no,
or
no, no, no. This is multiple. Yeah,
okay, okay,
that
okay.
that was
Mm-hmm.
this space problem. So
Mm-hmm.
yeah.
Okay,
So
okay.
this is QA.
Mm-hmm. Okay,
Hmm.
it is. Uh,
Yeah,
it should be.
yeah. So I'll use this part, the second one, for the answer. So we have now this information, that this is p minus 1, and we have something we don't know about this, but we for sure know that this is less than or equal to p. So this is less than, so this is equal to this, and this is less than or equal to p into p minus 1. We have this much information, but we also know that So that we have already seen. We have also know that this is equal to qa. So this is other part, this is, so I am using both of these. So this is into p. We have already seen qa over q is p. So this implies p divides qa comma zeta p over q. So we have this information. P divides. And now let's use that. So P divides this L over Q, but P divides QA comma zeta P over Q. This implies P divides. Now you know that this is this factor, right? Okay. So this is this factor, and P minus 1, since P minus 1, P cannot divide P minus 1, that we know, because P is prime and P minus 1 is, when, like, P does not divide any number less than P. So uh, so we have so this implies qa comma zeta p. So P should divide the other part, right? And we know that this part should be less than or equal to P. So this implies it should be exactly P. And we are done. Is that okay?
Yes.
So
1 second.
yeah, so we have used to like equalities. We split it with respect to qa and q zeta p, these two types. And from one we got p should divide this l over q, and from other we used for the formula. So in that formula we know that p minus 1 is there, and there is this part. Okay, and we have proved that this other part is also less than or equal to p. So we have something qa zeta p over q zeta p, the extension degree of this, into p minus 1. And this first part is this first part is less than or equal to p, and we know that
So
this full factor should be divisible by p. We are done. Yeah. Yeah. So this implies, what do we have as a result, that L over Q. So we have this condition, and from this formula, so even I don't need to write like this, so we can just use, say, this star identity. This is equal to P into P minus 1 by star. Okay.
okay.
So that was the thing. So we have used what is everything with Galois extensions, and so now we got this is a Galois extension. Okay. Thus L over Q is a Galois extension. Okay. So now we have this by fundamental theorem of Galois theory, there is this 1-1 correspondence between subfields of L over Q and subgroups of G. And how one goes from the other? So you let's say you have some subfield M, then that should map to Galois group of L over M or M over Q. Okay, we can check this. So if you start with a subgroup, you should get fixed field of with respect to H of L. Okay, so let's see what do we get if we go from here to here. This should be fixed field of L over okay, actually this should be this, because this, that is always a Galois extension, so that is required. Because if L over Q is a Galois extension, then L over M will always be a Galois extension. That is also proved in fundamental theorem of group theory. Yeah, sorry, Galois theory. So we have one correspondence. How one can go from here to here? How so? Exactly. So we have exactly those many subfields as many subgroups we have of G. So that is of course finite because G is a finite group. We know that the cardinality is P into P minus 1. So this is a subfields will get to be finitely many. Right? So also, so that is something hard in the sense, note that, so like note that H is non-abelian. That is, sorry, H, not H, G. So how one can show, one can see that, firstly we have this isomorphism of groups also. We have this affine line now, affine line over Fp, that we have seen. So what we can do, we can just consider subgroups of affine line, and corresponding to that we can have any element of G, and from there we can, so we can consider some subgroup of affine line, corresponding to that we have some subgroup of G, and corresponding to that we have a subfield of L over Q. So we get from this everything. So that is something you can try it out. Yeah, what I was saying, G is non-abelian. How will you check that? Since we just consider how G is defined. A goes to where? A zeta. So let's consider sigma to be this. Just take zeta p only. Okay, don't take any power. That is also fine, right? So you take sigma to be, and zeta p maps to, let's say, zeta p square. Okay, and you take tau, some other map to be, a goes to okay, I'll modify if I will require that. I don't know, let's say zeta pq, and okay, I should consider that p would be, yeah, let's say this. So let's say this. So let's see what is sigma of tau. So sigma of tau of A, where A is mapping. So if you want to check if it is abelian or not, we'll try. We'll see what is sigma of tau and tau of sigma. So this is this. So tau of A is zeta p. Oh sorry, A zeta p square. Okay, and I'm assuming p is not equal to 2, otherwise this will become identity. So anyway, so this is this. Now sigma of this, sigma of A into sigma of zeta p square. Okay, so sigma of A is A zeta p square into, this is equal to zeta p square. So you'll get zeta p raised to power 4. Now let's see what do we get from here. Just check if I have done any mistake or not. Sigma of A is equal to A zeta p, and you'll get tau of A, tau of zeta p. So tau of A is equal to A zeta p into tau of zeta p is so you'll get A zeta p square and into zeta p. So you'll get Q, right? So this is not equal. So I'm assuming P is big enough, like maybe let's say 5. For smaller you can still find some element, maybe for 2 we cannot, but yeah, this is something, because for 2, if P is equal to 2, it's a cardinality is just 2, we cannot have something better than that or something. So as an example, if P is 3, then this is actually of cardinality 3 into 2, which is 6. And you can check that this is isomorphic to S2 cross, sorry, not S2 cross, S3. So this is not a abelian group. That is, maybe you can say, first example of non-abelian, because you have seen that cyclotomic ones we get only abelian groups. So this is one of the example of non-abelian Galois group. Okay, so what you can do, as I said, so even there is very good theory about affine. Okay, I mean, okay, so in terms of subgroups, as I said, you have to go from one to another. What you will consider? You will consider subgroups of affine line. Moreover, A1, so A1 of FP star, sorry, not F, so this, you can also see this is isomorphism with the AB, or maybe I'll just write in the notation UV01, where U belongs to FP cross and V belongs to FP. You can even see in the matrix form also. So this is also, you can verify that you have a group isomorphism between A1FP and with this matrix group. So again, you can try to find what are all the subgroups here, because matrix is always nice to see. So you can see all the subgroups here, and you can get the subgroups of Galois group, and hence you can get subgroups by this fixed morphism, like fixed field. So you just consider fixed field of the sub corresponding to that subgroup, right? Is that okay?
Scroll down the page.
Sorry?
Scroll down the page.
Okay. Yeah.
Yes.
So here we have just proved that this is non-abelian. So that is something. Now we have an example of non-abelian Galois group.
And if P is equal to 2 from...
So P equals to 2, it is not abelian, because non-abelian, because you know that so if P is equal to 2, this is the cardinality. So this is the cardinality of Galois group. Okay, so cardinality of G, so that is 2. So you know that there is no there is just one group up to isomorphism, which is just the abelian group Z2. Okay.
Yes.
So you can try to find all the subfields, and then you can have the answer. So I'll just move to the second question quickly, because I thought I'll cover it. But this is exact same question, but you just need to now you have a fixed example, that is like you can see, you can realize this. So you have this polynomial, and you can see that roots of this polynomial. So firstly, for the roots, so first question asks, so you have this F, determine the splitting field. So for a splitting field, what should we have? We attach all the roots, and we will get a splitting field, right? So this is you can think of this like this, and you can so the roots. So roots of this, how can you see? Firstly, you use this Dharacharya formula for x square, that will give plus 14 b minus b plus minus root b square minus 4ac by 2a, right? So you'll get 14 plus minus, you can take 2 common here, you will get 7 square, that is 49 minus 9 by 2. So this will be 7 plus minus root 40, that is 7 plus minus 2 root 10. And actually you can see this. So this is, you can write root 2 square plus root 5 square. So you can split as 2 plus 5, and then you can see this is plus minus 2 root 2 into root 5. So you can actually write it as this. So this x will be what? Root 2 plus minus root 5, and you have plus minus here also. So roots of x raised to power 4 minus 14x square plus 9 are root 2 plus root 5. Now you take plus. First you take plus of this, and you take both the options, and then you take minus of this, that is minus root 2 plus root 5, and this is minus root 2 minus root 5. So you have all these options. So if you remember, last time we did such kind of question like root 2 and root 3, or maybe in general root p and root q, where p and q are relatively prime. So if the roots are like this, so we calculated everything. Even we proved that this is a Galois group, and we proved everything there, right? Also note that in the previous question we had something like zeta p, and we have a. So we have proved that q zeta p comma a, this is a Galois extension, and you know that finite Galois extension is simple. So actually you can find one primitive element for which this can be generated. Maybe this can work, zeta p plus a, or some ca at least, zeta p plus ca, that can work for some c belongs to q. You can actually see that we don't need to prove, because that's what the hard part is, because we don't, now we know that if it is a finite Galois extension we will get something, some element, primitive element. We have done that even for this primitive element theorem. So we know that there will be some c, because what was the reason, like zeta p plus ca, so c could be from q. So we have so many subfields, and if it is a Galois extension it has to have finitely many intermediate subfields. So we have now the theory of uh, like subfields are finite, collection of subfields are finite. So we have all these things, and we can get the simple like we can get that primitive element using this also. So this is sub interconnected now. So similarly in this case, as I said last time, we did for root p and root q, right? So this is exactly the same question. You just need to work out for root 2 and root 5, and that is nothing like new. Is that okay? So you can complete this question using this fact now.